everyone, and thanks for watching Edupedia World Videos. In this video we'll start a new topic called heat transfer. As the name suggests, heat transfer is the transfer of heat. What is heat? Heat is defined as the energy flowing from a high temperature body to a low temperature body, right? So when you put two bodies in contact and they have different temperatures, the body with the higher temperature is going to give heat to the body with lower temperature. The higher temperature body will have its temperature coming down and the lower temperature body will have its temperature rising until eventually both of them are at the same temperature, which is a state we call thermal equilibrium. So there are three processes by which heat transfer can take place, and I think learned of heat transfer in 7th or 8th class, I don't remember, very basic, but there was an illustration they used in the textbook which I always found to be quite easy to understand, so I'm going to use that. Let's say there are 4 people. One of them has a book and they need to give that book to the person at the end. This is the analog of one body transferring heat to another body. You can do that in three particular ways. The first way is conduction. The second way would be convection. And the third one would be radiation. Conduction primarily takes place in solids, although it can take place in liquids and to a much smaller extent in gases as well. In conduction, what happens is every molecule transfers heat to the next molecule. That molecule transfers heat to the molecule next to it, and in this particular process the whole rod will have its temperature increase. For example, if you have a steel rod and you heat it, so there's supposed to be a fire, if you heat it at one end, not immediately but eventually the other end will get hot. The process through which this happens is conduction. These molecules are in contact with the fire, they will get hot first. Remember, what is heat in terms of molecules? It is just vibration, right? So when these molecules get hot, they'll start vibrating very fast. That will make the molecules next to them start vibrating, which in turn increases their temperature, which in turn causes the molecules next to them to vibrate, and in turn eventually the molecules at this end will start vibrating as well, which means the temperature of this end will increase as well, right? We know this doesn't happen equally well for all materials. For example, if this rod is made of wood instead of steel, the temperature at this point would not rise very much, and that comes to the material and the thermal conductivity of the material, which we'll deal with in a moment. So conduction is the process by which every atom moves its neighboring atom or transfers heat to its neighboring atom, and in this process heat is transferred. In this particular case, it would be the analog of person A giving the book to person B, the person B giving the book to person C giving the book to person D. That would be a mechanism of conduction. Remember, there is no actual motion of material in conduction. When you heat this particular part and this particular part gets hot, no one molecule from this particular part actually moves to this end carrying heat with it. There is no actual motion of the material except for the small vibrations around their equilibrium positions. Convection is different from this. In convection, it is the only medium of heat transfer in which there is an actual movement of material. So let's look at and this is more frequent in liquids and gases. So let's say we have some liquid and we are boiling it. Sorry, I can't really draw fire. Yeah, let's say we have a liquid and we are boiling it. So what happens is the lower part of the liquid gets heated up first. Now there is some conduction happening as well. For example, the lower part of the liquid will get heated. it will start vibrating faster. It will cause the upper part of the liquid to get heated a little bit, which will cause the liquid slightly above it to get heated, and eventually the topmost part of the liquid will get heated as well. So there will be some conduction, but that is not the major form of heat transfer in liquids. What happens is, when we heat the lower part, its temperature will increase, which will cause its volume to increase, which will cause its density to decrease, right? As the density of the lower part decreases, it actually moves up. That's why when you heat water, you actually see bubbles. What are bubbles? Bubbles are air pockets which are at the bottom of the liquid, and they are moving to the top because as their temperature increases, the density decreases. So when you're boiling water, it is not like a rod where every particle transfers heat to the next particle. The actual material is in motion, and molecules which are hot are actually moving from point A to point B, transferring heat along with them. The analog of that would be, instead of passing to the next person, this person himself actually goes to this person and gives them the book. Right, so there is an actual movement of material in convection. Radiation is the third one, in which there is no medium required. Of course, there is no movement of material as well, because that is only true for convection, but both conduction and convection require a medium. In conduction, if we just heat this particular end will get hot because the heat is traveling through this rod. If there was no rod and we heat this particular end would get slightly hot because we increase the air temperature, but not very much. Right? So conduction and convection both require a medium, whereas radiation does not. Radiation can travel through free space. Radiation is the medium by which the heat of the sun approaches us. There is no medium between the sun and the earth, it's empty space, but still we feel hot because of the sun. So the medium for that is radiation. And the analog in this case of radiation would be, the person doesn't move, doesn't give the book to the next person, the person just throws the book, and this person actually catches the book. That would be analog of radiation, in which heat just goes from point A to point B, traveling through free space. Right. We are going to look in detail in this video on conduction. The next video will be about radiation. Convection is not that important. Also, it is not that quantifiable. It is quite hard to study conduction mathematically, at least not at this level, whereas conduction and radiation have been extensively studied mathematically. So let's start with conduction. So let's say I have a rod which has a length L, it has a cross-sectional area A. Let's say two ends of the rod are at different temperatures. Let's say this end is at T1 and this end is at T2. Right? And let's say T1 is greater than T2. That means let's assume that initially the rod was at T2, then I lit a fire at this point to make it T1. Obviously, eventually, the heat it all will have the same temperature. I'm talking about an intermediate state. So when this temperature is T1, this temperature is T2, and T1 is greater than T2, through the medium of conduction, heat will flow from the left to the right. Right? We know heat is a form of energy, so its unit will be joules. So the equation governing this process is delta Q by delta T. Delta Q is the heat transfer. This T is the time, right? So we are talking about heat transfer per unit time. That is equal to Ka by L times T1 minus T2. Now, the very first thing I'll say is, keep in mind the difference between capital T and small t. Small t is time, capital T is temperature. Right? What is K? K is the property of a material and it is called thermal conductivity. So if I have a steel rod and a wooden rod, and I have the two ends at different temperatures, heat will transfer much faster in the steel rod compared to the wooden rod, because steel has a much greater thermal conductivity than wood. That is why the bottom of the pans are made of steel, because they can conduct heat very fast, whereas the handles of pans are made of wood, so that you don't feel hot when you pick it up. So this is the equation which governs all of conduction. It can be written in a slightly more differential form, and that is delta Q by delta T, which is the heat transfer, is equal to Ka dt by dx. This is true when we know that the two ends distance L apart are separated by a temperature T1 and T2. Whereas in some cases we might not know at the two ends, we would know what dt by dx is. dt by dx is a quantity called the temperature gradient. It just means as you move a little bit towards the right, what is the change in temperature? If the change in temperature is very high when we move a slight amount, then the heat transfer would be very high between those 2 points. If the temperature gradient is small, then the heat transfer would be small. Right? We can actually package this equation in another way that makes it seem pleasing to us, and that would be, let me just show it to you. So delta Q by delta T is equal to Ka by L T2 minus T1. We can also write it as, sorry, T2 minus T1 or T1 minus T2, doesn't really matter now. So we can write it as T2 minus T1 is equal to L by Ka times delta Q by delta T. Now we need to really look at the structure of this equation to understand the power of it. Right. T2 minus T1 is the difference between temperatures. If we have any 2 points, they have different temperatures, then T2 minus T1 will be the difference in temperatures. What is delta Q by delta T? It is the heat flowing from one point to another point per unit time, obviously. Right. So T2 minus T1 is the change in temperature between these 2 points. Delta Q by delta T is the heat flowing through these 2 points, and L by K is a constant of proportionality. So this does seem to us to be a lot like Ohm's law. V2 minus V1, or delta V if you prefer, is equal to IR, or V is equal to IR simply. V is the change in potential difference which causes a current, and R is the constant of proportionality between the two. T2 minus T1 is the change in temperature which causes the heat, and L by Ka is the constant of proportionality. So just like R is called the electrical resistance, L by Ka is called the thermal resistance. Right. So we can actually write this equation as, and I'm going to write it now as, V is equal to IR. I'm going to use the same terminology, and R in this case is simply L by Ka, geometrical quantity depending on the length, the area of cross section, and the material. I is the current flowing, V is the temperature difference, not the potential difference. Right. The advantage of this particular formulation is that we can use a lot of results which we've already used for V is equal to IR. I'm sure you're familiar with the concept of series and parallel connections, so let's look at them. First of all, what happens in series connections in electricity? In series connections, the current is the same, whereas the voltage adds up. Right? The same is true in thermal resistances. So for example, let's say I have two temperature baths. A temperature bath is just a technical term for a particular container which has a constant temperature. We don't need to worry about the mechanism by which we maintain that temperature. So this is a temperature bath keeping things at temperature T2. This is another temperature bath keeping things at temperature T1. This would sort of be the analog of inner circuit having a battery which creates a voltage difference of V2 minus V1 on the two ends, right? So let's say we have one rod connected, then we have another rod connected, then we have a third rod connected, and then we have a fourth rod connected. L1, L2, L3, L4. This has an area of cross section A1, A2, A3, A4, K1, K2, K3, K4. So we have 4 rods. Now we know that the heat coming from this end, let's assume T2 is greater than T1, heat will be transferred from this end, it will move to this end. And we know any current going from one place has to come out the other side, right? Because we know that the temperatures are kept constant, so the temperature of any particular point will be kept constant, right? So the current is the same in all these 4 rods. Whereas the temperature difference adds up. If this is T2, this is T1, let's call this T alpha, T beta, T gamma. Then the temperature difference here is T2 minus T alpha. Here it's T alpha minus T beta. T beta minus T gamma and T gamma minus T1. If you add them up, the temperature difference is T2 minus T1. Right? So the equations here would be, I'm just going to write L by Ka is equal to R, equivalent to R. That means this L1 by K1 A1 is equal to R1, L2 by K2 A2 is equal to R2, and so on. So for the first one, we can write T2 minus T alpha is equal to I, the current, times R. For the second one, we can write T alpha minus T beta, this is R1, sorry, is equal to I times R2. T beta minus T gamma is equal to I R3. T gamma minus T1 is equal to I R4. We can add them all up. T alpha cancels, beta gamma cancel, and what we get is T2 minus T1 is equal to I times R1 plus R2 plus R3 plus R4. Now you can probably see why this formulation is valid. This means that this particular system is equivalent to another system which has one temperature at T2 and the other end at a temperature T1 and only has one rod where the resistance of the rod is R1 plus R2 plus R3 plus R4, which means we can say that for series connections R equivalent is equal to R1 plus R2 plus R3 plus R4. I'm sure you've seen this result in Ohm's law many times, that when you have series connections, the equivalent resistance is the sum of the individual resistances, right? So we've just derived it again, and we've used the exact same things. Just V doesn't mean potential difference, it means temperature difference. I doesn't mean current, it means heat transfer, but that doesn't really change the mathematics of it all. Lastly, I'm just going to show you the parallel connections as well. So we have this temperature T1, a bath. A bath could just be like a furnace, right? Let's call this T2, T1. So we have one rod, we have two rods, and we have a third rod. This is a rod, this is a thicker rod, and this is another rod. Again, L1, I'll just use R1, R2, and R3 now. So now the temperature difference is the same in all of them, but the current is adding up. The total current that T2 is supplying, by the way, when I say current now, I mean heat current or heat transfer, not electrical current. The total current that is supplied by this is the total current that is absorbed by this, and that is the total current that is the sum of these three currents. So in parallel connections, I adds up, whereas V is the same. So the equation we'll get is T2 minus T1 is equal to I1 R1, T2 minus T1 is equal to I2 R2, T2 minus T1 is equal to I3 R3. It's best that I take this down, 1 by R1, 1 by R2, 1 by R3, then this goes. Now we add these three, I1 plus I2, I3 plus I3 will be the total I. So I is equal to T2 minus T1, 1 by R1 plus 1 by R2 plus 1 by R3. But it should be equal to T2 minus T1 by R equivalent. So we've derived the result which I'm sure you've seen before, that for parallel connections 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3. So that completes conduction. Let me just say a little bit about convection, even though it's not really in your course, and then we'll move on to radiation in the next video. There are two types of convection: free convection and forced convection. Free convection is when the heated material moves itself due to a difference in densities, right? So when you're heating water in a bowl, the bottom of the water gets heated first and it automatically moves up because of the difference in densities. No one forces it to move up. So that is the example of free convection. On the other hand, if you have a blower, for example, a heater which pushes hot air out, that is forced convection, because in that case the hot air is being forced to push out by another external quantity. It is not simply moving to the top due to a difference in densities. So these are the two forms of convection. Another form of forced convection would be a hairdryer, right? It blows hot air, but the air does not flow due to a difference in densities. It is forced to flow by the mechanism of the hairdryer, right? In the next video, we'll move on to radiation. Thank you.